I'm now moving on to page 190 to 191. And for the questions in this video homework guide, I need to use the first derivative test to find all relative extrema, and I need to determine where they occur. All right, so for all relative extrema, this is just determining where the max and where the min points are, and we also need their coordinates, and then that will satisfy where the max and min occur. All right, so for these kind of problems, I need to start off by taking the derivative and then setting the derivative equal to 0 to find my critical numbers, and then I need to create a number line in order to find the max and min points. All right, so let's take the derivative right here, so y prime. The derivative of x cubed is going to be 3x squared, and then the derivative of 3 over 2x squared, if I use the power rule, this 2 and that 2 will cancel off, giving me a 3x. And then the derivative of a constant is just going to be 0, so that doesn't matter there. Okay, and then after I've taken my derivative, I notice that I have some like terms here, so I can factor out the common factor, and the greatest common factor here is going to be 3x. So if I factor out a 3x, I get x plus 1, and then I can set that equal to 0. Okay. When I have my 3x here, the value that makes this equal to 0 is x equals to 0. And this expression right here, x plus 1, if I set that equal to 0, x would be equal to -1. So these right here are the critical numbers, or the critical points, and then these are the numbers that I can put on my number line here. So above here, I will create a number line here, and I will put -1 here and 0 over here. And just below my number line, I'm going to rewrite the derivative expression as 3x times x plus 1. And now I need to find numbers in these regions. And the numbers in these regions, I need to pick any number in those regions, and I need to plug those into my derivative expression to determine whether those regions are positive or negative. Let's start at the very tail end here. I need a number in the green region, so maybe a number like 5 would be okay. So let's take 5 here. And if I plug in 5 over here, I get a positive expression. And if I plug in 5 over here, I get a positive expression. So positive times a positive gives you a positive result for the green region. And I can erase all those. And then the blue region, I need to pick a number that's between -1 and 0. So a number that could possibly work is the number -0.5, and if I plug that over here, -0.5 plus 1, that would give me a positive result. And if I plug in -0.5 over here, -0.5 times 3 would give me a negative result. So if I take a negative and times it by a positive, then I would get a negative result. So the blue region would be negative. I can mark it in like that. All right, and then finally I can look at the yellow region, and I need to pick a number in the yellow region, and maybe a safe number in the yellow region could be -10. So if I plug in -10 over here, let me just erase that, -10 plus 1, well, that would give me a negative result. And if I plug in -10 over here, 3 times -10 would give me a negative result. And a negative times negative gives me a positive result for the yellow region. Right, so that right there is the derivative test, establishing that number line. And once you have your number line established, then you can determine whether the max and mins are. Okay, so whenever you go from a, over here we have a positive to a negative, that's like going from a positive slope to a negative slope. This means we have a max right here. And if I go from a negative slope, so this part here is negative, so if I go from a negative slope to a positive slope, that means there's a min here. So there's a min right here. Okay, so now we need to establish the final results. I have a max at x equals to a -1, and I also need to determine the coordinates of that maximum point. So if I go back and plug in -1 into the original function, so this is the original function here in purple. So if I take this -1 and plug it back into the original function, the value that I get is 5 over 2. So the actual coordinate of the max is -1 comma 5 over 2, and this is a relative max. Okay, and then I have a minimum at x equals to 0, and if I plug in 0 back into my original function, I get 2, so my minimum is going to be at the point 0, 2. And that's how you would finish off the results here. So you would state that there's a maximum at x equals to -1, and the coordinate is -1, 5/2. And then I also have a minimum at x equals to 0, and the actual point is 0, 2. And that would finish off that problem. Okay, let's move on to the next one here, question number 4 here. So let's start off by taking the derivative right away. Actually, before I take the derivative, one thing that you should notice is that when you have a ln function, the domain of a ln function is x is greater than 0. So we might need to consider that when we're establishing our number line. All right, so let's go ahead and take the derivative. So y prime would be, well, the derivative of ln x is 1 over x. And then this expression right here, 1 over x, 1 over x is the same thing as x to the power -1. And if I take the derivative, the -1 here would come out to the front, so it would be negative x to the power of -2. So I can write that as -1 over x squared as my derivative. So let's just move that over here now. So my derivative of that would be -1 over x squared. Okay, now we need to take our derivative and set that equal to 0. Okay, so now we need to simplify this expression right here, and one of the ways where you can simplify this is that you take your x squared and then you can multiply it with the 1 there. So 1 times x squared is x squared, and then you can take this x here and then you can multiply it with this -1, giving you a negative x, and then finally you can times the denominators together, giving you x times x squared, which is x cubed. So that's one way where you can get a common denominator right away and write this as one entire fraction. And then on the numerator, there is a greatest common factor there. I can factor out an x, and that would give me x minus 1 all over x cubed. And then if we keep on simplifying here, this x and that cubed will cancel off. And then finally I would have 0 equals to x minus 1 all over x squared. So that's my most simplified version of the derivative. And once I simplify that, let's analyze this. If I set the numerator equal to 0, that would mean x would equal to 1. So that's one of my critical numbers there. And if I look at my denominator here, the value that makes the denominator equal to 0 is x equals to 0. So if x equals to 0, the denominator is 0, and then therefore the entire derivative is undefined. And remember, critical numbers happen when the derivative, or they happen when we have x values that make the derivative equal to 0 or undefined. So these right here are my critical numbers here. And then once I have my critical number, I can establish my number line here. And let's go ahead and plug those numbers on the number line. So there's a 1 here and a 0 there. And at the start of the problem, we did establish that the domain is x is greater than 0. So we're only interested in these regions between 0 and 1 and anything past 1. So those are the regions where we need to test on our number line. Okay, let me just erase all this. And let me just write my derivative expression just below the number line so that I can figure out the regions where it's positive or negative. If I start working on the green region, a number that we can pick over here is 10. And if I take the number, sorry, that 10's not really clear. Maybe I'll pick the number 9. If I plug in 9 into here, the numerator is positive, and the denominator is always positive. So in the green region, the region has to be positive. Okay, let's erase that. And then if I pick a number between 0 and 1, maybe a very safe number is 0.5. If I plug 0.5 into the numerator, I do get a negative result. 0.5 minus 1 is a negative result, and the denominator is always positive. So a negative divided by a positive gives you a negative result in the yellow region. Okay. All right, so after that, we can establish that when we go from a negative to a positive, that means we have a minimum here. So we have a minimum at x equals to 1. And after that, we need to figure out the actual coordinates. So our original function was y equals to ln x plus 1 over x. So I need to evaluate f of 1 because I need to find out where the y value is. Ln of 1 is going to be 0 plus 1 over 1 is 1, so the y value is 1. So that means we have a minimum at x equals to 1, and the actual coordinate would be 1, comma 1. So that one is there. Sorry, that one is there, and this one is that one right there. Okay, so that concludes that particular problem, and then we can move on to the next one. All right, question number 5. So for question number 5, for this kind of a problem, I have a fraction here. So if I take the derivative, I need to use the quotient rule. So the derivative of the numerator is e to the x times the denominator, which is just a single x. And then the quotient rule states that I need a minus sign. And then I would times by the numerator times the derivative of the denominator. So the derivative of x is just 1. And then I divide this by the denominator squared, so that would be x squared. And then I take my derivative, and then I set that equal to 0. And then I would have e to the x times x. And then I would have, well, this whole thing, e to the x times 1 is just e to the x. Not much I can do there, but notice that I can definitely factor out an e to the x. So if I factor out an e to the x, I would get x minus 1. So I can now remove all that and write down e to the x times x minus 1. And then I can start analyzing this and determine where my critical numbers are. Okay, so if I take this expression right here, x minus 1, I can set that equal to 0. If I do that, x would equal to 1. That's one of the critical numbers. If I have e to the x, if I take e to the x and set that equal to 0, an exponential function never touches the x-axis. So what that means is this result never gives you a 0 result, so I can just ignore that. And then finally, you should also look at the denominator here, x squared. If I take x squared and set that equal to 0, that means x equals to 0. So this is another critical number that I need to look at because I'm looking at values of x that make the derivative equal to 0 or make it undefined, and this is the x value that makes the derivative undefined. So those are my critical numbers there. Okay, let's go ahead and plug those numbers onto the number line, and let's evaluate what's happening here. Okay, let me put the numbers 0 and 1 here, and then just below this I will write out the derivative expression, which was e to the x times x minus 1 all over x squared. And I need to pick numbers in the yellow region, the blue region, and the green region. Okay, so one thing that we should also recognize here is in my derivative expression, if I take a look at the denominator here, the denominator is always going to be positive, so I don't need to plug numbers into my denominator. And if I look at this part right here, the exponential part, if I plug in any x value for that, so any like number to the power of 2 or 0 or a negative number, that will always give you a positive result as well. So I don't need to worry about this part or this part when I'm plugging numbers into my derivative expression from the number line. Okay, so let's pick a number in the green region, maybe the number 9 again. If I plug in 9 here, 9 minus 1 is a positive result. All right, so that was pretty easy. That one's done. And then in the middle here, I think the obvious number would be 0.5. If I plug in 0.5 into this derivative expression, 0.5 minus 1 is a negative result. So that one's done. And then finally, I can pick a number on the left-hand side here, maybe like -5. So -5 minus 1, that's going to be -6. So this expression right here is going to be negative. Okay. And then I can erase all that because my number line is done. And erase that. Okay, so over here, I guess I would have a minimum at x equals to 1. I have a minimum because I go from a negative to a I go from a negative result to a positive result, so there's a minimum there. And over here at x equals to 0, I go from a negative to a negative, so that's not a max or a min. Actually, this is going to be a vertical asymptote because if I go back to the original problem, this is the original problem right here. We do have a vertical asymptote at x equals to 0, so we can just put that on the number line right here. The VA is right there. So I can now finish off by saying there's a minimum at x equals to 1, and after that I need to find out the corresponding y value there. So if my original function is y equals to e the x over x, and if I evaluate f of 1, that's going to be e to the 1 over 1, which is just e. So the minimum is at x equals to 1, and the actual point is 1 comma e, and that is a relative min, by the way. Okay, that takes care of that problem. Now we can move on to the next one. These questions are quite long. Once again, I need to take the derivative again. So notice that there's two functions that are being multiplied with each other. So y prime, I need to use the product rule. So the derivative of x squared is 2x times the second term, which is just e to the power negative x. And then the product rule states that I need to add the first term, which is x squared, and then the derivative of the second term, which is e to the negative x. And the derivative of negative x is just 1, so I need to put a negative 1 there at the very end. Okay, and if I just clean this up here, plus and a minus sign, that would make this result negative, so negative x squared bracket e to the negative x. And then this would be 2x times e to the negative x, and then this would all be equal to 0. And if I highlight this e to the negative x and e to the negative x, that's a GCF, or it's a common factor, so I can pull that out as e to the negative x. And then if I take a look at, there's 1x here and there's 2x's there, so I can factor out an x for sure. So x times e to the negative x is my GCF, and if I pull that out, I would get 2 minus x, and then I would make that equal to 0. Okay, let's go ahead and figure this out here. This part right here, 2 minus x, if I set that equal to 0, that would mean x would have to equal to 2, so this is one of my critical numbers there. And for this part right here, x times e to the negative x, this part right here, the exponential part, that never equals to 0, so I can just erase that. And then when does x equal to 0? Well, that happens when x equals to 0, so that's another critical number there. Alright, so let's go ahead and write out our number line now. So my number line is like that, and then I can plug in the critical numbers here. So the critical numbers were 0 and 2, and there's 3 regions, a yellow region, a green region, and a blue region. And just underneath here I will write out my derivative expression again, which is x e to the negative x times 2 minus x. And when you're looking at your derivative expression, this part right here, the e to the power negative x, regardless of what number you put that in there, that's never going to be a negative result, so I can just kind of ignore that. It's not really important when I do my my number crunching here. Okay, so in my blue region, I will pick the number 9 again. So if I plug in 9 here, 2 minus 9 is going to be a negative result. And then if I plug in 9 over here, I get a positive result. So a positive times a negative gives me a negative result. So this is going to be a negative in this region right here. And then I can erase this. And then in the middle region, I will pick, maybe I'll just pick 1 here. If I plug in 1 here, I would get a positive result. And if I plug in a 1 there, I would get a positive result. And a positive times a positive is a positive result. So that's going to be positive in the green region. Erase all that. And then finally, in the yellow region, I'll pick negative 5. And if I plug in negative 5 over here, that's going to be 2 plus 5. 2 plus 5 is going to be positive, and if I plug in negative 5 here, that's going to be a negative sign, so a negative times a positive gives you a negative result. Okay, so I'm done my first derivative test now. My number line is complete, and then from my number line here, I can just pretty much find the maxes and the mins. This is going to be a minimum right here because I'm going from a negative to a positive, and then I have a max here because I'm going from a positive to a negative there. And then I can just write a final sentence here saying that there's a minimum at x equals to 0. And for x equals to 0, my original function was y equals to x squared times e to the negative x. If I plug in 0 back into my original function here, that's just going to give me a 0 for the y value. So the actual coordinate is going to be 0, 0. So there's my min. And then I have a max at x equals to 2. And if I plug in 2 back into the original function here, that's going to give me 2 squared times e to the power negative 2. 2 squared is 4, and e to the power negative 2 is the same thing as e squared. So 4 over e squared. So my coordinate here would be 2, 4 over e squared, and that's a relative max and a relative min. Okay, let's move on to another question now. I think this one will be the last question for this particular video. Since I have a fraction here, I need to use the quotient rule when finding the derivative. So let's start off by writing out y prime. And now the derivative of the numerator, 2 minus x, well, the derivative of that is going to be negative 1. And then I would multiply that with the denominator, which is x squared plus 5. And then the quotient rule states that I need a minus sign. And then I can write out the numerator, which is 2 minus x. And the derivative of my denominator is going to be 2x. And then I can divide that by the bottom all squared. So x squared plus 5 all to the power of 2. Okay, now that I've taken my derivative, I do need to simplify a few things, so I can distribute this. If I distribute that, I would get negative x squared minus 5. And then if I distribute this 2x times 2, that would be 4. That would be 4x, but then there's a minus sign there, so that would be negative 4x. And then finally, if I distribute the 2x onto the negative x, that would be negative 2x squared, and then this negative and that negative would give me a positive 2x squared. And that's all being divided by the denominator, all to the power 2, and that's being set equal to 0. Okay, from there on, I guess we can collect the like terms here. So if I collect those guys, 2x squared, 2x squared minus x squared, that would just give me a single x squared, so that would be just x squared. Those are gone. And then the negative 4x can tag along, and then the negative 5 can tag along, and then this is all being divided by x squared plus 5 to the power 2, and then I can set that equal to 0. And then on the numerator, this is a trinomial, so you can definitely factor that. So we need two numbers that multiply to negative 5, and those two numbers need to combine to negative 4. That's going to be negative 5 and 1, so x minus 5 times x plus 1. And I can just erase this now and replace this now with x minus 5 and x plus 1. So quite a bit of algebra that you have to do with this problem to set it up so that you can actually find the critical numbers here. On the denominator here, the denominator is always positive, so that won't give you any critical numbers there. But x minus 5, that one's not too bad. That means the critical number has to be x equals to 5. And this part right here, x plus 1, that means the critical number there has to be x equals to negative 1. So here are my critical numbers. And then I can plug those onto a number line like this, and I can plug in the negative 1 and the 5 there. And then once again, I have a few regions here, one in yellow, one in green, and one in blue. And I will rewrite my derivative expression underneath it as x minus 5 and x plus 1, all divided by x squared plus 5 to the power 2. Now, I did mention this already, but the denominator here, this is always going to be positive, so that's not really going to be important when I'm doing my first derivative test. So I can just kind of erase that because it's not really necessary. It's always going to be positive, so it won't help me. Okay, so in my blue region, let's pick the number 9 again. So if I plug in 9 here, this will be a positive result. If I plug in 9 over there, that's going to be a positive result. So a positive times a positive would give me a positive result in the blue region. All right, and after that, I can erase that. And then in my green region, a very safe number that you can pick is probably the number 0. So if I plug in 0 over here, 0 plus 1 is going to be a positive result, and 0 minus 5 is going to be a negative result. A negative times a positive is going to be negative, so the green region is going to be negative. I can erase that now. And then finally, in my yellow region, I can pick the number -5. And if I plug that over here, that's going to be a negative result. And if I plug a -5 over here, that's going to be a negative result as well. So a negative times a negative gives me a positive result. Okay, we're almost done here. We just need to make a final conclusion step here. This means I have, there's a max here. From positive to negative is a max, and then there's a min over here. A negative to a positive is a min. So now I can write down there's a max at x equals to -1. And then I need to find the actual y coordinate to complete the problem here. Now my original function was y equals to 2 minus x all over x squared plus 5. If I go ahead and plug in -1 here, I guess I would get 2 plus 1 all over -1 squared plus 5, and that would give me 3 over 6, which is going to be 1/2. All right, so the coordinate here is -1 comma 1/2. Let me erase that. And then I also have a minimum now at x equals to 5. And if I plug in 5 over here, that would give me 2 minus 5 all over 25 plus 5, and that would give me -3 over 30, which is -1 over 10. Okay, so to finish that off, I have a relative min at 5 comma -1 over 10. Alright, so that concludes this video. It's quite long, but some of these problems require quite a bit of algebra, and whenever you have a first derivative test, most of these questions will take at least a half a page to finish, just because there's quite a bit of work to do. Alright, until next time.